2008. Following the graduation, he gained valuable industry experience as a practicing engineer, working on the design, rehabilitation, construction, and risk assessment of infrastructure, particularly buildings and bridges. From 2008 to 2010, he worked as a field engineer with the Earthquake Reconstruction and Rehabilitation Authority, where he played a key role in post-disaster infrastructure development. In January 2011, he joined the CNW department as an STO and was promoted to executive engineer in 2019. In 2024, he was promoted to superintendent engineer, a position he still holds. Engineer Zeeshan completed his MSc in 2013 from UET Peshawar by defending a thesis on the retrofitting of unreinforced confined brick masonry building using ferrocement Wali. He later enrolled in the PhD program at the Department of Civil Engineering, and after successful completion of his coursework in 2020, he commenced his research under the supervision of Professor Dr. Shahzada. The title of his PhD research is Risk, Resilience and Sustainability-Based Assessment of RC Structural Systems. Throughout his academic journey, Engineer Zeeshan has made significant contribution to the field of risk and sustainability of infrastructure. He has authored 3 impact factor journal articles on vulnerability of non-structural elements and seismic capacity assessment of unreinforced concrete block masonry buildings, furthering the understanding and development of this specialized field. His REC committee comprised of Professor Dr. Shahzada, who is supervisor as well as chair of the committee, Dr. Rehman Sahab, who is director DAMS of Hydropower SMEC Engineering Consulting, as member from the industry, Dr. Zeeshan Ahmad, postdoctoral researcher at the Department of Civil and Environmental Engineering, Hong Kong Polytechnic University of China, who is member from other university, myself as member from the same department, Dr. Akhtar, Associate Professor, Industrial Engineering Department, UET Peshawar, as member from another department, whereas the foreign thesis evaluators are Dr. Yu Dong, who is Associate Professor in Structural Engineering in the Department of Civil and Environmental Engineering, Hong Kong Polytechnic University, and Dr. Engr Tomic, who is postdoctoral researcher at Swiss Federal Technology Institute, Switzerland. So with this, I would like to call Engineer Zeeshan on stage to present his work.
Thank you very much, sir, for the nice words and introduction. Let us start with the presentation. The topic of our research study is Risk, Resilience and Sustainability-Based Assessment of RC Structural Systems. I will start with this outline of presentation. I will start with introduction, the problem statement, the objectives of our research, the methodology, as well as the results and discussions, followed by the conclusions and recommendations, and in the end, the references that we have used. Before going to the introduction part, kindly focus on this animation showing 2 different types of building. We can see that under the ground shaking, the non-structural components, that is the infill walls which are associated with the RC frame buildings, as well as the furniture and architectural finishes, they are the most vulnerable. Code-based building design, they can ensure that catastrophic damage of the building can be avoided. However, the non-structural elements, they undergo significant stresses, and therefore, due to different nature of the non-structural components, they are most vulnerable and can pose a serious life safety issue to the public, as well as the functionality of the building thereby compromises, and therefore the vulnerability study for the assessment of these different structural and non-structural components is important for amicable seismic risk resilience. Now, relating this with the different construction practices that is used, these are different images from the under construction buildings in Peshawar. We can see that there is a non-uniform method of construction. In some, the bare frames are first constructed, followed by the infill walls, either in the shape of partition walls or in the shape of facades. And in some, there are glass facades which are normally used in commercial buildings, and also the architectural finishes. Another common thing to note is that soft story effect is also prominent, which is mostly in the commercial buildings due to the entering of the people inside the building. So this phenomena has from the past earthquakes been seen as the main vulnerability aspects, and the functionality of the building therefore is at risk during the real earthquakes. Now some earthquake scenarios to highlight this impact. For example, this is from the Nepal earthquake of 2015. We can see that in plane wall, their presence has induced the different nature of damages. Also, due to the failure of the infill wall, the short column effect is prominent, thereby causing the failure in the RC members also. Even for a low-rise building, for example, from the Peru earthquake of 2001, we can see that for G+1 building, such effects are there, and thereby risking the overall sustainability as well as the resilience by causing the vulnerability of the different components. So, to move forward, there is different approaches. First is the first generation performance-based earthquake engineering. They have FEMA 356 is one of the document that is prepared under those motives, and they have different performance levels for the RC frames with and without infill walls and different components. And these are the different drift ratios that is associated to determine the performance level. Based on this, the performances under the level of earthquake, whether it is a service level earthquake, design based earthquake, or the maximum considered earthquake, it is also seen. And under the different level of earthquake, the failure of the buildings can be therefore assessed. From the building functionality and the performance, the fragility curves are then drawn, which is expressing the probability of exceeding a particular damage stage. And based on the different performance levels, the fragility curves can be then drawn. And fragility curves can be a useful tool for the construction of the vulnerability study. And from the vulnerability curves, which is dependent on the three parameters, that is the social, economic, and physical properties. And based on this, the damage ratio can then be determined, which is the ratio of the cost of repair to the cost of replacement, and can be used as a decision variable for the decision making and retrofitting strategies. Now, to compare the performances of non-structural elements in terms of the classifications, they can be either displacement sensitive, acceleration sensitive, or a combination of the both. The infill walls, they are sensitive to story drifts in the in-plane direction, whereas sensitive to the acceleration in the out-of-plane direction. Based on the different codes, one of them is the FEMA P58. They have highlighted that the non-structural elements, they have the maximum contribution to overall cost before and after construction. And based on their documents, the partition walls, which is considered as a non-structural element, they have more than 50% weightages, whereas the structural element, it has weightages of less than 20%. Even after damages, the same is more for the non-structural components. And from one of the research document by the National Institute of Standard and Technology, NIST, USA, they have reported that even after 50 years of earthquake, similar damages have caused similar types of similar earthquake has caused similar types of damages, which necessitates the need for further research. And if you want to increase the resilience for important buildings, that is the hospital or the school, you can then use some sort of innovations to enhance the performances. Comparison of the code performances for the structural elements and the non-structural elements. The design provisions, they are conditionally applicable for majority of the non-structural components with a limited mass ratio. The performance criteria are not specified for majority of the non-structural components, as well as the ductility, they are based on ad hoc values and not on actual scientific testing. And the load criteria, the loads are normally scaled down. And the level of safety, it does not ensure that the non-structural elements, they remain functional after the occurrence of an earthquake. Resilience can be the property which determines the ability of a structure to undergo damages, and the ability to restore from this is then you can determine the seismic resilience, and it is based on the different properties which is taken from the literature and as shown in the flow chart. To link the resilience with the sustainability, it is important to perform the life cycle assessment, and these are the different steps you can perform for assessment of the life cycle assessment, and the different steps that is involved in the different fabrication of the project. For example, the product stage, the construction stage, the end stage, and which is one of them is the embodied impact, and the other is the circular economy. These guidelines can be used for the carbon footprint at different stages of the project, and both at the construction and post-construction stage, thereby linking the vulnerability with the resilience as well as sustainability. Sustainability is based on the three important parameters, that is the social, environmental, and economical. And these are different formulas that can be used as per the European standards and the Royal Institute of Chartered Surveyors guidelines for calculation of the carbon footprint at the production stage, transportation stage, construction stage, and end of life stage. And further, the social impact is calculated in two ways, that is the time required for the repair and the social cost of carbon. Now, coming to the problem statement, the RC structural system, they have different challenges in accurately modeling the effects under the in-plane, out-of-plane, as well as the combined effect, and therefore, under different loading conditions, their performances therefore need to be assessed. Further, the current design codes, they have mainly focused on the outcome and the performances of the structural members, thereby the non-structural components, their determination of the actual properties are often excluded in the design practice. And it is important to integrate the risk and resilience with the sustainability by performing the life cycle assessment so as to have a suitable decision making approach and for optimization of the project decisions. And these gaps that are highlighted, it is then the objective of our study to address these gaps by performing different experimental as well as numerical analysis and also the life cycle assessment to determine the carbon footprint also. Now, the objectives, the first objective is to investigate the seismic performance of the infill walls in the in-plane and the out-of-plane direction using the experimental as well as numerical testing, and to investigate the effect of the openings and the interface properties on the seismic performance for the determination of the component-based fragility for further practical decisions, and to link the risk and resilience with the life cycle assessment using the LCA techniques, and to develop the risk priority number framework, which can be a suitable guideline for the practitioners based on the performance of the structure, which can be helpful for determination of the risk category as well as the performance in terms of the score rating and the relative color code, which can give you a suitable guideline. That methodology, we have two-phase methodology. One is the experimental and the other is numerical, which are further subdivided in the two respective phases. The first phase includes the shake table test in the out-of-plane direction for the RC frame with different masonry infill walls and opening combinations. And the second is the quasi-static test of 3-floor 1/3 scale building under the displacement control environment. And the numerical, it includes the in-plane pushover analysis using the RC frames with different set of infill walls and openings, and the time history analysis of the RC frame with infill walls, so that the acceleration as well as the displacement properties of the RC frames with infill walls can be then determined. And this is then used for the determination of the risk and the resilience as well as the sustainability, further for the development of the risk priority number. Now, coming to the experimental phase first, the first phase that we discussed in the previous slide, these are the model descriptions and the material properties that are used for the half-scale RC frame with infill walls and different opening configurations. These are the different steps that were involved in the fabrication of the model and its transportation to the Earthquake Engineering Center. These are the models that are used. One is the solid infill wall, other has a side door combination of infill wall, other is center door opening, and the other is the combination of the door and the window, and the last is the center window. These are the typical opening that we found in any residential building. So the different combinations are therefore taken for assessment of their local effects, so that their overall global capacity can then be determined. And these are the bottom images shows the instrumentation plan showing the installation of the accelerometers and the displacement transducer at different levels under the shake table test, so that the readings can be recorded and used for the analysis. From the free vibration shake table test, the first parameter is the free vibration response, which gives you the input in terms of the energy dissipation as well as the damping. For the different models, the damping calculated are shown, and the respective values that we have obtained by using the free vibration response and the peak of the values, it gives you the damping characteristics. Next is the shake table results in terms of the top accelerations that we have recorded after the results, and the different values that we have obtained for each model, and the peak values which are encircled as shown. The acceleration properties, they are mainly higher for the solid infill walls, and as the openings increases, the acceleration response is then reduced. On the other hand, with the larger openings, the displacement capability has been seen to be more for the infill with openings, and when you have a different set of opening position but the same opening percentage, the variation in the results are also seen. Now these are the different damage pattern that we obtained. The shake table test, it was using the sinusoidal frequency domain under the frequency control, starting from a frequency of 0.5 hertz, and with an increment of 0.5 hertz is what extended. The time interval was 15 seconds, and the top initial mass loading is also shown. The damage pattern that we have obtained highlighted the critical impact of interface and the junction of the infill wall with the RC frames, as well as the location of the opening. Thereby, due to the damages in the infill wall, the damages in the RC frames are also seen. These are the final damage pattern showing the location of the interface opening as well as the presence of the opening and their crack distribution. The blue color shows the part of the wall that was not majorly damaged after the shake table results. Now, the second methodology was the fabrication and testing of a 1/3 scale 3-floor building. These are the different steps that were involved in the casting of the model and its transportation to the Earthquake Engineering Center for conduction of the quasi-static test under displacement control environment. And this is the final model that was fabricated for testing. These are the different floor plans as well as the beam and the column cross sections, followed by the location of the walls as well as the marking of the different displacement gauges on the wall. As per the similitude law, you have to place additional inertial mass, and these were placed on different floor levels so as to we be in complete agreement with the requirements of the similitude laws. The displacement control environment testing was started with the intensity of 0.5 mm, and it was repeated for 3 cycles, and during each cycle the positive negative loading was recorded, and it was given an increment of 0.5 mm until major structural collapses were seen in the or damages were seen in the different walls and the models of the building. These are the final damage patterns that we have obtained. We can see that connection between the RC column as well as the staircase, it also we can see that they opened up. The west wall, which was the back side wall, it has the maximum opening. So major damages in the infill walls were there, thereby also causing cracks in the RC columns as well as around the opening. The crack intensity is shown. The bare frame, it also exhibited cracks, and in the beam column joint, which is normally a critical parameter for the seismic analysis, they also exhibited these different types of cracks. From the quasi-static result, the hysteresis curve as well as the force deformation curve were plotted. The initial steep slope of the hysteresis curve, it indicates the increase in the stiffness and the strength, possibly due to the presence of the infill walls, and due to the brittle nature of the masonry. After reaching the peak load, as the infill walls fails, there is a sudden drop in the curve as seen in the force deformation curve, and the test was therefore stopped at this point so that the model can be retrofitted for the future research studies also. From the force deformation curve, the binilinear idealization is used for the calculation of the energy dissipation, and the different performance level, that is the immediate occupancy, life safety, and the collapse prevention, were then plotted against the respective drift ratios. Immediate occupancy was obtained at a drift ratio of 0.6%, life safety at a drift of 0.95%, and collapse prevention at a drift of 1.1%. Further, the impact on the damping with the increase in the drift is shown. It can be seen that a very low drift, that is 0.1%, there is a sudden drop in the damping, and it continues to decrease with the increase in the drift. Further, it is very important to extend the quasi-static results to actual earthquake scenarios, and therefore different studies are there. One is the FEMA P58 PACT, which uses the SPO tool by converting the quasi-static results to the incremental dynamic analysis, thereby simulating the performances under different levels of earthquake. As the non-linear time history analysis, it is a very costly method, and therefore cannot be used for such high multi-story buildings in, due to different costs involved and the fabrication and the testing requirements. So we have used the N2 method, which is based on the capacity spectrum method, and it uses the FEMA P695 22 sets of far field ground motion, and by using the different intensities, it has a PGA greater than 0.2 G, P ground velocity greater than 15 centimeter per second, and a soft soil type assumed is as a soft soil of soft rock or stiff soil. And from this, the engineering demand parameter, which is based on the second generation of performance-based earthquake engineering by using a decision variable, we have used it for the determination of the story drift against the intensity measure. From this, it is then used for calculation of the performance levels. And here, instead of the FEMA 356, we have used the HAZES manuals, which has the slight damage state, moderate damage state, extensive damage state, and complete damage state. It thereby gives you a very good prediction of the component-based fragility. If you want to be focusing on a particular component, you can use it for the determination of the fragility and its shift under the different performance level. Thereby, the different performance levels are then calculated and shown as in the graph. From the fragility curves, normally some research studies, they end up the work with the calculation of fragility function, but it is also very important to calculate the vulnerability so that the resilience can then be calculated. The vulnerability curves, it shows that at the increasing intensity of the ground motion, there is the loss of a function, and as we increase, there is a higher losses, thereby highlighting the need for either repair due to heavy retrofitting or reconstruction of the project. From the vulnerability curve, one aspect we discussed was the fragility curve, which expresses the probability of exceeding a particular stage. The other function is the probability density function, which is a more detailed description and a derivative of the fragility curves, and it is used for the determination of the likelihood of a particular damage stage. You can see that the overlap of the different performance level in the graph of the different performance levels, and beyond a specific limit, then we move to the collapse stage of the model. And the resilience curves on the right shows the impact on the functionality under the different levels of the intensity measure. Initially, it has a more of a horizontal slope, thereby indicating that resilience is higher. But then, as the intensity increases, there is a sharp drop in the resilience, and thereby reducing with the increase in the intensity measure. Now, the second phase of our model was numerical modeling to extend the studies for different parametric studies. Then the Diana FES software was used for performance of the numerical modeling, and the images shown are the RC bare frame model and the loading condition as well as the mesh model and the loading condition replicated from the experimental studies and the analysis option that is used. The damage pattern for the experimental as well as numerical modeling is shown. Compared to the experimental studies, the numerical model, it offers you a wide range of different description by giving you results in terms of the deformation, the reinforcement strength, as well as the crack fits. In addition to this, based on your area of research or your area of interest, you can avail other different options that are available and can be utilized based on your requirements. From the results of the numerical modeling of the Peshawar analysis, the force deformation curve is plotted, showing the initial stiffness, the peak load, as well as the final deformation, along with the hysteresis curve showing the energy dissipation and the at the different levels of increasing deformation, and the positive and the negative cycles shown. Further is the use of infill walls with side door opening, and we can see that compared to the previous case, we can see an increase in the initial stiffness as well as the peak load, but due to the brittle nature of the masonry, there is a reduction in the deformation capability in comparison with the bare frame case. Now, when we have a center door opening, we can, and the same opening size, that is 27% opening, we can see that force deformation curve, it differs from the previous curves by showing more ductility, but the strength capability is reduced as compared to the previous case. By further extending the study to increasing the opening size, that is using a door and window combination, this is 38% opening, and we can see that ductility has further improved by increasing the deformation capability, but the strength capability is thereby reducing. If we reduce the opening size, that is using a centralized window, we can see that the strength increases more and the deformation capability is also more, but it is still lower than that of the bare frame case. Further, the extension of the force deformation curve was used for the use of the bilinear curve using the ASC code techniques for the, calculation of the immediate occupancy, life safety, and the collapse prevention. Compared to the bare frame case, we can see there is a very sudden shift from the performances of the life safety to collapse prevention. So thereby indicating that the post damage resilience for the case of infill walls reduces with the use of the infill walls, and thereby although the strength capability is more, but in the initial stage due to the induction of the masonry, it aids in the increasing the initial stiffness and the strength capability, but the brittle nature and the failure under brittle nature, it causes the sudden shift from the life safety to collapse prevention stage. Further comparison of the results in terms of the different levels of performances that we have obtained in terms of the loading capability as well as the displacement capability is shown, and the results show that compared to the bare frame case, for the last case, that is the side door side window opening, we can see that the strength increases twice as compared to the previous case, but the displacement capability has reduced. And by increasing the opening size, we can see that the strength gain is almost the same as that of the bare frame case, but the deformation capability is reduced. And for the set of opening, that is when we have the side door opening and when we have a centralized door opening, we can see that the results vary by both in terms of the strength gain as well as the displacement capability. Further, the extension of the study was the use of effect of the opening, and as we increase the opening, we can see that the strength as well as the effective stiffness they reduces, but yield displacement it is slightly shifts between the high and the low, between the 20% to the 50% mark, and further it continues to increase with the increase in the opening size. Then another parametric study was the use of different infill thickness. We have used the 4.5-inch wall as well as 9-inch wall, and we can see that the results vary at different levels. For example, between the 20 to 30% in case of the yield displacement, as well as in the initial 20 to 30% in case of the maximum load, and the effective stiffness also initially it varies and then slightly varies, but otherwise they match well, and both the infill thickness they show a same sort of trend and same sort of results. The second phase of the numerical modeling was to perform the time history analysis. For this, three strong earthquake records, that is the Kobe earthquake, Loma Prieta earthquake, and the North earthquake, was selected, and scaling them from different intensities between 0.5 G to 4 G, with an increment of 0.5 G were used for the calculation of the time history analysis, as well as the further for its use in the incremental dynamic analysis. Displacement response from the time history analysis shows that for the bare frame case, at a lower intensity of ground motion, there are reduced displacement, and as the intensity increases, the displacement increases. Same is the case when we have the infill walls with different opening combinations. Although the infill walls, their presence, they reduces the displacement capability, and the openings, the infill walls with lesser opening, they shows the reduced displacement both at the lower ground motion intensity as well as the higher ground motion intensity. This is animation showing the performances under the time history analysis. This is for the bare frame, and we can see that the non-presence of infill walls, it can causes the localization of stresses around the beam column junction, and also the effects are there which causes the cracks in the RC members, and it further extends to both the bottom and the top with increasing in intensity. When we have the infill wall, that is the side door opening infill wall, we can see that the cracks first generate in the due to the stress increase in the infill walls. The presence of the lintel beam, it also adds to the stiffness, and upon exceeding the capacity of the infill walls and the failure, then the cracks extend to the RC member, but the crack generation, it is still lower than that of the bare frame case. When we have a centralized door opening, we can see a symmetrical distribution of crack generation from the four corners of the infill walls, and then it extends to the column, and again the crack intensity in the column is lesser. When we increase the opening size, that is by using a combination of door and window opening, we can see a higher intensity of cracks in the infill walls, and thereby more magnitude of cracks in the RC members, but they are still lower than that of the bare frame case. When we have reduced the opening size by using a center window option, we can see that the cracks generation is again around the four corners, and they then extend to a different portion of the infill walls. But due to the lesser intensity of the opening, the crack intensity in the RC frames are much lower as compared to all the previous 4 cases. From the time history analysis, the incremental dynamic analysis is then used for the generation of the IDA curves. As per the UBC 97 ATC code and the NIHR code, they have recommended to use 3 minimum ground motion records, and we have used the minimum 3 ground motion records. And the IDA curve, they shows the performances under the different levels of drift against the respective intensity measure. The flatness of the curve, they indicate the point of failure, and at the flat nature of the curve, at this point, a slight increase in the intensity of the earthquake, they causes a higher drift values. And when we use the infill walls, we can see the slope of the curve changes, and it requires a more intensity of ground motion to cause the failure. And we can see that the openings with a large proportion, that is 38% opening, we can see that the slope of the curve almost resembles that of the bare frame case. And as we have lesser opening size, we can see that the slope of the curve, it changes, and the flat nature of the curve is thereby avoided. The openings having a lesser magnitude, it has a totally higher, the slope is different, and it needs a different magnitude of intensity to cause failure. From the IDA curves, the fragility curves are drawn, which expresses the probability of exceeding a particular damage stage. The performance levels in terms of the immediate occupancy, life safety, and collapse prevention are then drawn. And we can see that for the bare frame case, there is uniform shift between the different performance level in terms of the IO, LS, and CP point. Whereas in the case of the infill walls, we can see that the performances shift, and there is a larger gap for all the cases of infill walls. The openings with the lesser size, they showing a larger gap. And on the other hand, the shift between the life safety to the collapse prevention is very gentle, very sudden for the case of the masonry infill walls compared to that of the bare frame case. So, indicating that the post-damage resilience thereby reduces due to the introduction of the infill walls, although for bare frame, they still has a larger margin compared to that of the infill walls. From the fragility curve, the vulnerability curves are then drawn, which expresses the damages in terms of the mean damage ratio against the respective intensity measure. The MDR, they, as discussed in the introduction, it is used for the determination of the performance indicators in terms of a damage variable. By multiplying the MDR value with the cost of the project, you can get the total replacement costs, and by multiplying it with the number of people, you can get the casualty rate. Further, it is important to extend the risk and the vulnerability assessment in terms of the life cycle assessment, thereby performing the sustainability study. For the model that we have experimentally tested, the construction phase carbon footprints are shown, and it can be seen that the conventional brick, they have the higher carbon footprint exceeding more than 2000 kilogram carbon dioxide. If you opt for the alternative material, that is using the ram earth brick or the concrete blocks, you can reduce the carbon footprint by 25 to 50%. And also at the post-damage stage, after repair of the damaged model, you can again see that the carbon footprint is higher for that of the brick masonry and compared to the other the items that are used. And when you use the recycled reinforcement, you can then reduce the carbon footprint to a certain limit. The social cost of carbon before and after damages are shown, and it can be seen that after damages, the cost not only reflects the social cost impact in terms of the currency, but also the loss to the community in terms of displacement, as well as the loss of the function for important buildings, commercial buildings is also very important. So the minimum the social cost of carbon after damage, the better it is for the community resilience. Further, it is important to develop a risk classification system, and for RPN, risk priority number, we have used it based on the different literature studies. For our case under consideration, by using the combination of the severity, occurrence, and detection, and this score is then used for the performance indicator against the respective earthquake. For example, if you have a low intensity, you can get a low score, and as the nature of the earthquake, the damages are more, you get a higher value of the RPN. Now, we have proposed this framework for the inventory management. This can be used for, since it is learned from the literature that for non-structural components, it is very difficult to get the exact data, and the inventory management is therefore very important. So these are different steps that can be used. For example, defining the objective and the scope, the classification, whether the structural elements or the non-structural elements, the data collection by using different surveys, the risk and the resilience, as well as the prioritization, sustainability, and its validation. Now, coming to the conclusions from our study, the in-plane vulnerability, they are higher with the increase in the opening size, and it has been found to have the maximum with the increase in the opening size. And opening of around 40%, they shows a higher vulnerability, and the major structural failure can then therefore be expected. Similarly, in the out-of-plane direction, by increasing the openings instead of the solid infill wall, we can see that response acceleration reduces, and a percentage reduce of 38% is therefore observed. And similarly, the same opening combination but different location of the opening, they can vary results in terms of the response displacement as well as acceleration. Further, from the fragility curves, we can see that there is a sudden shift from the life safety to the collapse prevention in case of the presence of the infill walls, possibly due to the strut and time mechanism or of the infill walls during the earthquake intensities of ground motions. Further, sustainability study shows that the carbon footprint is higher for the brick masonry, followed by the other materials that are used, and therefore suitable alternative material can be used to reduce the carbon footprint by 25 to 50%. And the failure mode effect analysis and failure mode effect and criticality analysis techniques can be used for the determination of the RPN, which can be a useful tool for a valid guideline and decision making post the disaster for the disaster resilience and the recovery planning. And the good correlation between the experimental and numerical study, it shows that the RPN metrics and the results that we have used can be used for the prediction and the performance indicator, and can for the practitioner engineer, they can be used in the field of practice. Now, some recommendations for the industry based on our research. The framework that we have developed, it can be used for good inventory and as well as the classification of the elements and to perform the different steps related to the risk, resilience, and the sustainability. In order to minimize the risk and the resilience vulnerability, it is very important to plan and design your openings in such a way that they reduces the impact of the damages rather than increasing due to the geometrical orientation of the opening. And the in-plane and out-of-plane effect infill wall is very sensitive to the interface connection, and therefore for improvement in the seismic performance, it is important to adopt suitable measure for better connectivity between the structural elements and the non-structural element, that is the infill wall in our case, so that to improve the seismic performances. And the RPN tool that we have developed, it can be used as per the FMEA and FMECA approaches, and since it is a novel approach, it can be improved with the further research in this area, and therefore open for further improvement in the field of practice. Based on our study, the recommendations for the academia are in order to assess the overall performance of the non-structural elements, it is recommended to use a shake table test with different non-structural elements, that is the HVAC, the claddings, which are higher vulnerability in terms of their damage causing the life safety issue, so that their vulnerability can be determined and more precise information related to its behavior can then be observed. And using of alternate material instead of the conventional brick masonry, so that the carbon footprint can be reduced, although the soundproofing and other properties which have the benefit in terms of the brick masonry, they should not be compromised. And the use of the recycled material, so that to minimize the waste, reduce the depletion of the resources, and increase the sustainability. With that, these are the references that are followed. I thank you all for listening, and I come to the end of my presentation.